Hello everyone, I'm Baiyang from the Chinese University of Hong Kong. Today, I'm going to talk about our work AutoGTCO graph and tensor co-optimized for image recognition with transformers on GPU. This is a joint work with collaboration from COHK and SmartMall. The talk is divided into 6 parts. In the first part, I will tell the introduction of our work. In the second part, I will share some related work and background knowledge to help readers understand our work. In the third part, problem formulation will be introduced. And in the fourth part, I will give the overview of our system to implement graph and tensor co-optimize. The fifth part will be something about our evaluation results. The final part is a conclusion we get in this work, which can guide the future research. Okay, let's move into the introduction part. Deep learning models are widely used in our daily life as for image processing and computer vision. We have convolutional models. As for the language processing, we have LSTM models. As for data relationship modeling, we have graph neural networks models. It is important to deploy these models efficiently. For the deployment of these models, we have lots of modern accelerators, such as NVIDIA GPU, AMD GPU, Google TPU, and GraphCore IPU. However, is deep neural network inference in current deep learning frameworks or libraries while utilizing the underlying hardware accelerators? The answer is obviously no. Take NVIDIA TensorRT as an example. In order to get the high performance computing and efficient deployment on NVIDIA GPUs, it has two steps in graph level optimization. In the first step optimization, the vertical fusion of operators is introduced. Lots of common operators such as convolutional 2D, batch normalization, ReLU are combined into a big kernel, which can reduce the data moment in the inference section. We can see the optimized results in the vertical fusion image. In the meantime, horizontal fusion is also processed for data reuse. As we can see from the horizontal fusion part, 3 CBR branches have the same input, so they can be fused into a single branch for the input data. It can reduce lots of overhead between the kernel launch and memory communication. Computation of the operator is parallelized through the threads in a GPU kernel. If we want to run this operator efficiently on GPUs, overall, CNN-based models can achieve high performance execution on NVIDIA GPUs by TensorRT. Let's have a look at TVM. TVM is a state-of-the-art deep learning compilation stack. It has lots of different layers, which can interact with each other for high performance scheduling. On the top of the stack, there are lots of different deep learning frameworks such as TensorFlow, PyTorch, and MathStat, and Caffe. The computation graphs obtained from these different deep learning frameworks will eventually be converted into a graph-level intermediate representation. In TVM, it is called relay, and then they will generate lots of paths operations for the computation graph. After the graph rewriting, we can get the optimized graph. This is graph-level optimizations used in TVM. For the tensor level optimization, TVM uses the idea which is similar to the highlight. It decouples the algorithm and schedule, and can support lots of different backbones, including NVIDIA GPU, ARM CPU, Intel CPU, and ASIC. Our workflow follows the same pipeline to TVM. Now, let's have a look at the related work and background section. In this section, I'm going to talk about some work about image recognition and GPU, which could enhance our understanding of our work. What is image recognition? In computer vision, it is defined as a collection of image classification, object detection, and pixel segmentation. The pixel segmentation can be divided into two categories, semantic segmentation and instance segmentation. Currently, transformer models have been integrated into the image recognition task because of the simplicity and universality. In the image classification task, vision transformer attains excellent results compared to the state-of-the-art convolutional networks, while requiring substantial fewer computational resources to train. In object detection, DETR demonstrates accuracy and runtime performance on par with a well-established and high optimized fast RCN model. In the meantime, a sequence-to-sequence prediction task with transform models has been adopted by semantic segmentation. It achieves new state-of-the-art on lots of data sets. So what is transform model? The transform model is the first transduction model relying entirely on self-attention to compute representations of its input and output without using sequential, aligned RNN, or convolutional. Attention fields can be described as a mapping of query and a set of key value pairs to an output, where query keys and outputs are all vectors. The output is computed as a weighted sum of the values. We can see from the left figure that scaled dot product attention is composed of matrix multiplication and softmax operators. From the right figure, multi-head attention allows the models to jointly attend to information from different representations, subspace, and different positions. Deep learning models are often trained and executed on the GPU. Modern GPUs employ a complex execution pipeline and memory collector to support concurrent execution of parallel threads. Take 2080 Ti GPUs as an example. It contains 6 string multiple processors. Each multiple processors include multiple single instructions, which we call SMT units. Each of them has multiple lines of execution. Threads scheduled in the same SMT unit are called a warp, which is the smallest scheduled unit in the GPU. Like a modern CPU, a GPU consists of multiple memory hierarchicals. The thread local registers are the fastest memory component, having the lowest access latency. The string multiple processor local L1 caches and shared memories provide a large storage capacity over the thread level register, but have modest higher accessing latency. All the three multiprocessors have a unified L2 cache. The off-chip global memory, similar to the RAM in a CPU system, provides the largest memory storage capacity on the GPU, but has the longest accessing latency. In this section, I'm going to define the important information in our work. So the first thing is a computation graph. A transformer model is defined by a computation graph J equals to vertical and edge, where V is a set of vertex and E is the edge set. Each vertex can represent an operator such as jam and softmax operators in the computation graph. Each edge UV belongs to E is to describe the dependency between U and V. And the second thing is the operator patterns for each operators. We have 5 operator titles in our work. The first one is injective type. The second one is reduction type. The third one is complex auto-fusible type. The fourth one is the element-wise type. And the fifth one is opaque type. And for the fusion strategy and schedule defined in our work, we define a schedule S of a computation graph as follows. S is a set which contains lots of pairs. In each pairs, it can contain 2 elements. The first one is V and the second one is F. So V represents a group of operators in the I space, and Fy is a pair to describe the fusion relationship between 2 nodes. Finally, computation graph can be executed on the schedule S from the first phase V1, F1 to last phase Vk, Fk sequentially. And our problem can be defined as follows. Given a computation graph G and a fusion schedule S on a VR GPU, our goal is to search for a schedule S star. So S star equals mean cost GS. So where cost is the latency of executing G according to the schedule S. And in the transform model, it has 2 important formula. The first one is the attention QKV. It equals to softmax Q times the transpose of K and over to square dk times V. And for the multi-head QKV, it equals to the head 1 to head H and contact them together times WO. Transformer model, we have noticed that transformer models have lots of softmax operators in the multi-head attention and can be fused with batch matrix multiple communication operators together. Okay, in this section, I'm going to have a look at our overview of our system. The row shows the float of the optimized subgraphs from the transform models and the tensor programs generations on GPU platform. Our tensor generation framework is composed of 4 important modules. The first section is a dynamic programming-based operator fusion. The second section is a subgraph scheduler. The third section is a CODA program sampler, and the fourth section is a performance tuner. Then let's have a look at the dynamic-based operator fusion. The input is a transformer-based model without any operator fusion, and the output is a collection of the operators with new tags. The function of this module is to find the optimized operator fusion schedule for the transformer model. If we can find a kernel that can do the computation of all the operators in the stage, we can just execute the kernel instead of launching many kernels one by one. This is the idea of operator fusion. Next, we can use an example to illustrate it. Here, we have 2 placeholder, input and output. We also have 3 compute type operators, matrix multiplication 1, softmax, and matrix multiplication 2. Operator fusion is not universally acceptable because we can't always find such a kernel that can do all of the computation in the same stage. However, it usually has better performance because it reduces the number of kernel launches and potentially reduce the memory access. We use usually here to indicate that sometimes it may be slower than the operators without fusion. For example, we may enlarge a kernel to make it fusible with other kernels, which increase the computation. In other words, if we fuse the compute bound operators with memory bound operators, it can improve the performance of the fused kernel. If we just fuse multiple compute type operators, it may degrade the performance of the fused kernel. In this example, we have 3 conditions. So as we can see from the below flowing image, in the first condition, set V has 2 operators, matrix multiplication 1 and softmax. Set V prime has matrix multiplication 2. Note that the matrix multiplication 1 and softmax are in 2 independent phases. The difference between the first condition and the second condition is whether matrix multiplication 1 and softmax operators are executed in the same phase or not. In the third condition, set V only has matrix multiplication 1. After the dynamic programming algorithm, we can get the final state that matrix multiplication 1 and softmax operators are fused into the one phase. Matrix multiplication 2 is executed in another independent stage. This formula describes how the AutoGTCO works. I will explain each component in the formula through the example of the computation graph. Here, we represent the operator of the computation graph we want to schedule. We use dpV to represent the latency of the optimal schedule for V. To find the optimal schedule, we evaluate all potential last stage V prime and converts the original problem into a subproblem that finds the optimal values schedules for V minus V prime. In this process, we need to measure the latency of the last stage V prime. We can definitely have the last stage of the optimal schedule enumerated. Therefore, we can find the optimal schedule through this dynamic programming algorithm. Then let's have a look at some components in these formulas in more details. The input of the subgraph scheduler is a transformer-based model with operator fusion, and the output is a collection of lots of subgraphs decomposed by the computer intensive operators such as matrix multiplication. And the function of the subgraph scheduler is that a subgraph scheduler can allocate time resources for optimizing multiple subgraphs generated by the DPOF. The input of the CODA program sampler section is a subgraph with fused operators, and the output of this section is a collection of CODA kernel code for these operators. The function of CODA program sampler is that it delineates a large search space and random samples various programs from it. Let's zoom in the CODA program sample sections. We can find that it is composed of 2 important functions. The first function is a sketch generations, and the second function is annotation. For the below figure, it is an example about batch matrix multiplication and softmax operator fusion. The sketch of generation is to construct the sketch structures for each operators, and the notion is assigned to random values for each position. Let's move into the performance tuner section. The input of the performance tuner is a sampled CUDA kernel code, and the output is the performance of the generated code. The function of this section is to train a course model that measures the performance of sampled tensor programs. We continued to follow the design of the auto tuner part in the TVM. Okay, let's move into the evaluation results. We use 3 benchmark models in our evaluation: DETR for object detection, SETR for semantic segmentation, VIT for image reclassification. The pipeline of our workflow can be summarized into 2 patterns. For high-performance computing library TensorRT, we use PyTorch to build models with different parameters, and then use OX export interface to obtain OX model. We use OX simplifier to simplify the OX model and then convert it to an excitable engine defined in the TensorRT environment. In terms of the compilation flow AutoGTCO, we first compile the model into the torch script format and then use a PyTorch interface defined in relay to relay. For the subgraphs, the corresponding tensor programs are generated by TVM code generation. And all of the experiments are done by the batch size equals to 1. Details of the model tests in this work are listed in this table, including the number of encoders, the number of decoders. We report all of the experiment results for batch size 1. We do the some experiments on the end-to-end performance testing. The baselines are PyTorch JIT, TVM with coding backend, and TensorRT and answer. So the software version of the baseline are for the PyTorch, we use 1.7.1 version. For the coding, we use version 7.6.5. For the CUDA, we use 10.0 version. For the TensorRT, we use version 7.0.1.011. For TVM, we use 0.8. As we can see from the table, compared with TensorRT, AutoGTCO can get 1.01 to 1.38 times speed up in the transformer-based model. And compared with answer, AutoGTCO can get 1.01 to 1.2.1 speed up. We also do some experiments on the subgraph benchmarks. The baselines are multi-head attention, encoder, and decoder structure of the DTRS-15 model with 6 encoder layers. Compared with the PyTorch JIT, AutoGTCO can get 2.47 speed ups on encoder and 11.67 on decoder. And compared with TensorRT, AutoGTCO can get 2.47 times speed up on MA multi-head attention, 1.08 times speed up on encoder, and 4.19 times speed up on decoder part. And compared with answer, AutoGTCO can get 1.29 times speed up on multi-head attention, 1.17 times speed up on encoder, and 1.17 speed up on decoder. In conclusion, we find that the graph level optimization defined by human experts missing the potential performance. We propose graph and tensor co-optimized AutoGTCO. Another dynamic programming algorithm is to explore operator fusion, new sketch generation rules, and the search policy for CUDA kernel generation are introduced. AutoGTCO can achieve 1.1 to 1.38 times speed up on diverse transform-based vision models. Thank you.